As the last speaker, I would just like to say how much I appreciated coming to this conference and how good it has been to meet with everybody here, and to thank Goran and the rest of the organizers for the really wonderful job they've done. So let's all give them. But rather than give some grand closing talk, instead I wanted to give a scientific talk on some work that I've done recently with a graduate student at Johns Hopkins Chief Charles. And what I'm going to be talking about is the theory of supersymmetric extra dimensions. By now well known, of course, that string theory predicts that space-time has these extra dimensions. In fact, during the last 5 years, we've come to realize that these extra dimensions can be large, even potentially large enough to be observed. They can be the size of an inverse TeV, they could possibly be as large as a millimeter, they can in fact be infinitely large, and we wouldn't have known. But string theory also suggests that space-time is supersymmetric, and that's my motivation for investigating the theory of supersymmetric extra dimensions. Now, I'm not actually going to construct real string models, but instead I'm simply going to listen to what string theory is trying to say, and use that then as motivation instead of following all of the details. Now the problem with supersymmetry in these higher dimensions is in fact it's very complicated. To my mind, the theories are quite formidable and the notation is impossible for at least me to penetrate. And there's also known superspace formalism for higher dimensions. And so for all of these reasons, model building in terms of higher dimensional supersymmetry is very difficult. So the solution that I'm going to talk about today is to describe higher dimensional supersymmetric theory in terms of four-dimensional superfields, where I take an ordinary superfield, which is a function of 4 dimensions and theta, and then lift it by including the higher dimensional coordinates, y. But from a 4-dimensional point of view, these coordinates y act just like an infinite set of extra indices labeling my superfields. So in fact, there's really no problem. The advantage of thinking about higher dimensions this way is that the formalism is simple. Everybody who does supersymmetry, at least, knows how to use n=1 superfields. But the disadvantage, of course, is that the manifest higher dimensional supersymmetry and the manifest Lorentz symmetry associated with the higher dimensions is lost, as we'll see. But it's a small price to pay. So in this talk, what I'm going to do is to focus on theories with 5 dimensions. First, of course, because the construction is the simplest. Or I could just simply imagine that the other extra dimensions are even smaller than the 5th dimensions. But also because a warped extra dimension is a natural explanation for the hierarchy, the difference between the Wien scale and the Planck scale. We'll see that actually n=1 superfields are very well suited to bulk plus brane constructions, where I have a 5th dimension, and these grains are slicing to the bulk. And in some sense, then, this label, y, just tells me which brane I'm on as I'm slicing through the 5th dimensional bulk. So the outline of the talk is as follows. I'm going to build up by starting by reviewing the situation with n=1 supersymmetry in 4 dimensions. Talk about matter couplings and gauge fields. Then I'm going to move up to n=2 supersymmetry in 4 dimensions. That's because 5-dimensional supersymmetry reduces to n=2 supersymmetry in 4 dimensions. And I'll show you how to describe matter couplings, hyperkähler matter, in 4 dimensions, n=2, in terms of n=1 superfields. Then we'll step up and consider 5 dimensions, talk about both the matter and the gauge fields in the 5 dimensions, and at the end, say a few words about how to translate this into the situation with warp geometries. All will be presented in terms of n=1 superfields. So let me start by thinking in 4 dimensions, just simple n=1 supersymmetry, the stuff in the textbooks. Matter in such theories is described in terms of chiral superfields, a certain number of chiral superfields, which contain a complex scalar, 2 bosonic fields, a Majorana or Weil fermion for each complex field, and then an auxiliary field F. In n=1 supersymmetry, these coordinates A, these fields A, are actually the coordinates of a complex manifold, a Kähler manifold, A Kähler manifold is basically a manifold which has a complex structure J that squares to -1. So I know what I is equal to, because it's complex, and it's covariantly constant on that manifold. Now, the action is simply, in superspace, the integral of d4x, the integral of d4 theta, the integral over all of this grasping coordinates, of some function, some real function of the fields, the superfields phi and phi dash. And in components, this action reduces to something that just looks like a nonlinear sigma model. A kinetic piece for the scalars, a kinetic piece for the fermions, and then higher order terms. The metric in the sigma model is actually given by two derivatives of the field of the real function k. So in a Kähler manifold, this is actually the relationship for the metric. The metric is given by two derivatives, the complex derivative of a Kähler potential k. And note, of course, that this construction is invariant under what are called Kähler transformations, where I take k and I shift it by an analytic plus an anti-analytic field. So in superspace, the integral of d4 theta of something chiral or anti-chiral is 0. And in components, you see that the metric, since it has both starred and unstarred derivatives, the metric is also invariant under those Kähler transformations. And so that's how the Kähler geometry is built into the n equals 1 in 4 dimensions. So the bottom line of this construction is that n equals 1 matter couplings in 4 dimensions are in one-to-one correspondence with these complex manifolds, these Kähler manifolds. The component Lagrangian is a nonlinear sigma model where the complex fields are the coordinates of this Kähler manifold. And the superspace Lagrangian is just the integral of this Kähler potential. And the matter couplings are all invariant under these Kähler transformations. Now, if I would like to do gauge theory, I need to talk about gauging symmetries. I have this nonlinear sigma model. What are the symmetries of the sigma model? Well, the symmetries of the sigma model are just the isometries of the metric. And so the symmetries are determined by the isometries of the Kähler manifold. And they're generated by analytic holomorphic Killing vectors, xi, a. It's a vector because it has a complex coordinate I, and then there are a of them, where a runs over the dimension of the gauge group. And in fact, on a Kähler manifold, these Killing vectors are gradients themselves of something called a Killing potential, D. And so we have these things which are generating the symmetries. Now, for simple groups, the dAs actually are completely fixed by the symmetries that are involved. And this is completely well defined. And when they're U1 factors, there's actually the freedom to shift these Ds by constants, by real constants. And these real constants are nothing but the Phi-Leopoulos term of n equals 1 supersymmetry. Anyway, so how do we do that gauging? These Killing vectors determine the gauge transformations of the chiral superfield. This is a chiral superfield interpreted in terms of superfields as analytic functions. These isometries are chiral as well, and I have A of them, so these are the parameters that run over the gauge group. So the lambdas are chiral transformation parameters that are the algebra value. To make the theory invariant, of course, you have to have a vector field as well. And the vector field has a gauge transformation as well, a non-abelian gauge transformation. This is just the ordinary gauge transformation in n equals 1 supersymmetry. So for an example, we can consider a U1 supersymmetric gauge theory with a single complex scalar field which I'll call Z. The Kähler potential is just K is equal to Z star Z, and the Kähler potential then is just 1. So this is ordinary normalizable U1 gauge theory. The Killing potential in this theory is just Z star Z as well, and so the Killing vector is just IZ, which corresponds to rotating, right, the field Z, the coordinate Z by a phase. And so the Killing vector describes a U1 rotation. So then the matter coupling, and well, it's easy to write down. We have the initial piece, which is the Kähler potential. We have a piece which corresponds to the kinetic energy term for the gauge multiplet. And then we have some coupling as well, which couples them all together that makes it gauge invariant. And in fancy notation, it can be written in some sort of West-Semino term. But really, when you boil it right down, for the simple case that we were just discussing about, this expression has a simple form. The initial Kähler potential was phi star phi, and so I subtract that off and replace it by the gauge invariant Kähler potential. So the top piece is actually what you look up in the textbooks, plus the kinetic so this is the coupling that we'd like to generalize to higher dimensions. And so as I said, I'm going to do it step by step. The first thing I'm going to do is to step up to n equals 2 in 4 dimensions, and then go up to d equals 5. Is the plan clear? So what I've done is drag you through the n equals 1 matter coupling in terms of superfields. And we've seen that it's described by Kähler geometry in 4 dimensions. N equals 2 matter couplings, of course, also have to be Kähler because n equals 2 contains n equals 1 as a subalgebra. So there's certainly some set of Kähler manifolds. In fact, they are called hyper-Kähler manifolds. They have more structures than just ordinary Kähler manifolds. So in what follows, I'll use these n equals 1 superfields because n equals 1 is a subset of n equals 2 to describe the n equals 2 matter. So let's begin by recalling that n equals 2 supersymmetry, the hypermultiplets, actually contain 4 scalar fields. And so in this construction, we'll need an even number of n equals 1 chiral multiplets. What we'll do is we'll take the Lagrangian to be just as it was as before, but we'll require that this Lagrangian be invariant under a second supersymmetry, besides the one that's manifest from the superspace. In fact, it's kind of fun to show that this action is invariant under this extra supersymmetry. This is a chiral field, so this d bar make sure that the site is chiral. This thing isn't really a superfield because it's screwing up the n equals 1 supersymmetry, that's okay. Omega is actually an anti-symmetric tensor that's covariantly constant, that has the property that it actually can be used to raise and lower the indices on the metric. And so sometimes omega itself is called the symplectic metric on the hyperkähler manifold. But it's just not hard to check. Here's the supersymmetry parameter for the second supersymmetry. It's not hard to check that this action is actually invariant under these transformations, provided these are anti-symmetric and covariantly constant. So these omegas can be used to define actually 3 parallel complex structures on the manifold. The first one, j squared is equal to -1, that's the one from the Kähler manifold, but I actually have 2 other ones as well, each of which squares to -1. And so the point about a hyperkähler manifold is it actually has 3 complex structures, and the manifold is Kähler with respect to each of them. Moreover, they obey an SU2-like relation, where their anti-commutator is delta, and the commutator obeys an SU2-like. Anyway, these omegas actually define what is called the hyperkähler manifold, and it's possible to check that the first 2 supersymmetries, the one that's manifest and the second one, close with each other without use of the equations of motion, so we're almost off shell, except that the commutator of the first and the second supersymmetries closes only with the use of the equations of motion, so we're not completely off shell, we're a little bit on shell here. Now in n equals 1 supersymmetry, you're always free to add a superpotential to this Kähler potential. S here is a phase, which you can usually, in n equals 1 supersymmetry, can be pulled into the superpotential, but I'm separating it out for the case that we're considering here. The question I'm now going to ask is, when can this construction with both a Kähler potential and a superpotential be lifted to n equals 2? Well, I claim for you actually that this action is invariant under the full n equals 2, where the second supersymmetry transformation is this now, the piece that I had before. And when S is real, a real phase, I have to add an extra term. The only condition is that the superpotential obey a particular condition. That the superpotential P, when I take its derivative and raise with respect to the symplectic metric, I get a vector which I call xi. And this xi has to obey a certain set of conditions. And these look an awful lot like isometry conditions, right? Isometries obey some sort of conditions that look like this. And in fact, this is called the x is really a killing vector. It's a symmetry of the manifold. It's actually called the triholomorphic killing vector, meaning that it's complex, it's holomorphic, it's analytic with respect to each of the 3 complex structures, each of the 3 definitions of I. So any superpotential can be added, provided it's related, its derivative is related to a symmetry, a triholomorphic killing vector, and it's n equals 2. So if there's more than one such killing vector, you can add any linear combination of the superpotential as well, and the transformation gets modified appropriately. So once I've added the superpotential, it's not, again, hard to show that the first two supersymmetries close without the use of the equations of motion. But the closure of the first and the second supersymmetry requires the equation of motion, and when you calculate it, you find something that looks like this, which is pretty interesting, because it's basically saying the supersymmetries close on the scalar fields into bosonic symmetries, as they should. Central charges are like bosonic symmetries. It closes into a bosonic symmetry, which is generated by this triholomorphic Killing vector. And so in this way, you can actually write n equals 2 sigma models in terms of n equals 1 superfields. And if you've actually ever looked at the way they're normally written down, this is much easier. So two examples. One example, again, let me consider a case of a flat hyperkähler manifold with two complex coordinates, x and y. So the Kähler manifold, I'll just take you through the simple thing, x star x plus y star y. When you do that, you find the symplectic metric is just what you think it might be, constant antisymmetric tensor. Three possible superfields are in this theory. And three possible superpotentials, I mean. They all obey the conditions. They each obey when you put gradients, become triholomorphic Killing vectors. In each case, as you can see, since the superpotentials are quadratic, they give rise to mass terms in the component theory. That's what you've already known in equals 2. It's possible to have mass. But you can even consider more complicated manifolds too. Here's a Higuchi-Hansen hyperkähler manifold that has a very complicated looking Kähler potential. So I have some sort of radius here, and I can write in terms of that radius. You can check still, in this case, the symplectic metric is still just the epsilon tensor. And actually, what's amazing is that in this particular curved Kähler manifold, I still have the exact same superpotentials as I had before. They still are triholomorphic Killing vectors, and they still generate masses.
So each of the superpotentials are equal to a different Killing vector then?
Each one gives its own Killing vector, and then you can take linear combinations of these.
As them up then.
So now we have the building blocks, and we'll step up and look at n equals 1 and d equals 5. First, I'm going to talk about how to lift the matter to 5 dimensions, and then we'll talk about adding the gauge fields, and finally move on to warp geometries. So the previous construction, as I said, can be lifted to 5 dimensions just by adding the fifth coordinate in here. As before, half of the supersymmetry is manifest, and half is realized as above by the transformations that I've shown. As we see, is again the advantage is that lots of people know how to manipulate these superfields, and the disadvantage is that the 5-dimensional Lorentz. So what I claim for you is that the correct Lorentz invariant action is given by something that looks like this. Here's the piece. I'm integrating over d5x now because I have 5 dimensions. Here's my Kähler piece, which would have been the kinetic curve in 4 dimensions. I need something else because I need some d5s if I'm going to have a kinetic piece in 5 dimensions. Turns out that this is the sort of thing you can add, where h is a very particular sort of analytic function. H is basically a potential for the symplectic structure. If I take the curl of H, I get the symplectic structure. This is the only condition that I need to get the right component Lagrangian. And so, in fact, there's an extra degeneracy in superspace. Any H whose curl gives omega works. It's fun to show, actually, that the supersymmetric transformation law doesn't change. This Lagrangian is still invariant under that transformation, provided H is the potential for the symplectic structure, and the symplectic structure is covariant to constant. The component Lagrangian is Lorentz invariant. You can make a 5-dimensional spinner out of the 2 4-dimensional spinners, and again, you would like to use this symplectic structure, and it works out just perfectly. Here, as you see, though, what I mean by the 5-dimensional Lorentz invariant is not manifest because I have some